Hello students, in this video I'm going to take this topic basics of carbohydrates. Before starting carbohydrate chemistry, when I will take these basics, then it will be very easy to understand so many things and get so many things with the concepts and especially isomerism. So let's get started. In basics of carbohydrates, first see the name carbohydrate. Name carbohydrate is telling you the molecular formula. Many times names are giving you such good information that you need not cram the things because name is telling you. See here, the name carbo means it has carbon. The name hydrate means it has water. Now put all this in bracket with N here. This is the molecular or empirical formula for carbohydrates. This is the molecular or empirical formula for carbohydrates. Now there is one more formula in carbohydrates which we have to do. That is number of isomers. Number of isomers for a compound is given by the formula 2 to the power n. The formula is 2 to the power n. Now be careful here, in both these formulas n is there. N is written, right? But let me tell you, this n is not same. This n is different. This n in case of molecular or empirical formula is number of total carbons. Take all the carbons like glucose. C6H12O6, take all the carbons, right? But this formula of isomers, this N is number of asymmetric carbons, also known as chiral carbons, right? So be careful in using both these formulas because this N is different in both the formulas, right? Now let's see what is a symmetric carbon. When any 2, 3 or 4 valencies are occupied by same atom or group of atoms, then the carbon will be symmetric, like CH2, CH3, CH4, that will be symmetric. Also, if 2 valencies are occupied by same group of atoms, let's say this carbon H here, R1 here, R1 here and R2 here, then this carbon is symmetric because 2 valencies are occupied by same group of atom, that is R1, right? Now tell me, C double bond O is symmetric or asymmetric? C double bond O. C double bond O, that is 2 valencies occupied by oxygen, that is symmetric. Okay, 2 valencies occupied by same atom oxygen, right? So let's write some general point about asymmetric carbon. That is, whenever a compound has asymmetric carbon, that compound will show both optical and structural isomerism. Both optical and structural isomerism. Or isomerism is because of asymmetric carbon, right? Now this is a general point. You can apply this point in any topic and you will be right. Okay, general point means you can apply this point in any topic. So let's see the structure of amino acid. The structure of amino acid. Amino and acid. When the see this name as if you're first time looking at this name, amino acid. Now, what do you mean by amino group? Amino group is NH2 group. Acid group is carboxy group, COOH group, right? Now, when they have given the name to the structure, they have not written acid amine. They have written amino acid because it has a meaning. The name has a very important meaning in it. See now, when I have written amino on left hand side, carboxy on right hand side, then I am going to join these two groups with a carbon in between, completing the valency of carbon with hydrogen here and a side chain here. You know, this is the structure of an amino acid, and whenever this amino acid is present in protein, this is the way it is present. That amino group is on left hand side, acid group is on right hand side. That's why the name amino acid. So whenever I will make the structure of this amino acid, then I will always make amino on left hand side, carboxy on right hand side, because this is the way it is present in proteins. In books when you see, then they will sometimes write amino here, sometimes they write amino here, sometimes they write here, like that they do. But I will be very uniform in my pattern of making the structure of amino acid, right? So now see, this central carbon is asymmetric. The amino acid central carbon is asymmetric. If it is asymmetric, that means amino acids show both optical and structural isomerism, right? So amino acids also show both isomerism. Now coming to the definition of carbohydrates, the definition is polyhydroxy, aldehyde and ketone. So there are 2-3 words in the definition. I'll be taking each word one by one and I'll be explaining so many points out of each word. So the first word is polyhydroxy. See, hydroxy means which group? OH group, and poly means many. So carbohydrates have many OH group. Now let's see some general points about OH group. So the first point about OH group is that whenever a compound has OH group, then that compound will be polar. Why it is polar? Because it will make hydrogen bonds. OH will make hydrogen bonds and therefore it is soluble in water also, right? So whenever a compound has OH group, that is polar, and whenever a compound has OH group, then it has tendency to bind phosphate. OH has tendency to bind phosphate, or we can say phosphate has tendency to bind OH. For example, whenever glucose enters a cell, then quickly it is converted to glucose 6-phosphate, now you know. Why? Because glucose is polyhydroxy, there are so many OH groups, number 6 OH group gets combined to phosphate, making glucose 6-phosphate, right? Because OH has tendency for phosphate. Now number 3 point is that whenever a compound has OH, then the suffix used is ol. The suffix is ol, that is ol written in the end of a compound, that means it has OH. For example, alcohol, glycerol, you can see ol written in the end. So that means it has OH, that means it is soluble in water, having polar component. Now see one more name, the name cholesterol. Ol written in the end, that means it has polar component, but you know cholesterol is a lipid. It has non-polar component also. So any compound which is having both polar non-polar component, that is known as amphipathic. So we can say cholesterol is amphipathic. There is no need to cram cholesterol amphipathic. The name is telling you, name is giving you information, right? Now these 3 points are general points about OH, but now a specific point for carbohydrates. When OH is there in carbohydrates, let's say a carbohydrate has 6 carbon, then number of OH will be 5 OH will be present in that compound. If a carbohydrate has 5 carbon, then number of OH will be 4. So can I say that number of OH is 1 less the number of carbons in case of carbohydrate, right? Now the other 2 words in the definition are aldehyde or keto. Either they have aldehyde group or they have keto group. These 2 are functional groups of carbohydrates. Functional means their function, their chemical reactions are done by these 2 groups. Either they have aldehyde group or they have keto group. Now let's see what is aldehyde, what is keto. Let's take a 3 carbon skeleton C1, C2, C3. In this 3 carbon skeleton, if double bond oxygen is present at C1, completing the valency with hydrogen here, then this group is known as aldehyde group. So can I say aldehyde group is always present at C1, right? Now again I am taking a 3 carbon skeleton. Now I am making double bond O at C2, valency is already complete, then this group is known as keto group. Keto group is always present at C2, right? So now I'll ask a question. Tell me, functional carbon is symmetric or asymmetric? Tell me. Functional carbon, symmetric or asymmetric? See, functional carbon, when I say, then I'm talking of both aldehyde and keto. That is C1 also, C2 also in this case with double bond oxygen. Functional carbon in carbohydrates is always double bond oxygen, that is symmetric carbon. So functional carbon is symmetric but only in linear configuration. Only in linear configuration it is symmetric, because in cyclic configuration it becomes asymmetric. That we'll be seeing later in anomerism, right? So we are done with the basics of carbohydrates. Now let's see the next video in which I'll be dealing with isomerism.